Hi, I'm Bob. Let's finish the remaining computer exercises today for Chapter 14, Advanced Panel Data Methods, in the textbook Introductory Econometrics, a Modern Approach, the 7th edition by Professor Jeffrey Woodridge. Let's look at computer exercise 15. The dataset covers murders and executions, capital punishment for 2,197 counties in the United States. In Part 1, consider the model and answer the question. Why does it make sense to include legs of the key variable executions in the equation? Executions have a deterrent effect on murders, and the process takes time. So the executions in the past few years might affect this year's murder rate. In Part 2, apply OLS to the equation from Part 1 and report the estimates of delta 0, delta 1, delta 2, and delta 3, along with the usual pooled OLS standard errors. Do you estimate that executions have a deterrent effect on murders? Provide an explanation that involves AI. We use the regress command to estimate model with pooled OLS. The capital L operator indicates the leg term of the variable. L2 means the second leg of the variable. I report the estimates and the usual standard errors for delta 1 to delta 3. Remember to include time dummy variables to represent a different intercept for each time period. The 4 execution variables have positive coefficients, implying a positive relationship between executions and murders. But it does not mean more executions result in more murders because the pooled OLS estimates suffer from omitted variable bias. The omitted county-specific factors such as education, the strength of law enforcement, and people's attitude towards the law, are captured by the county fixed effects, AI. The pooled OLS method does not control for the unobserved fixed effects. These unobserved factors affect the murder rates and correlate with executions. So the OLS estimates will be biased. Or we could think of it as an example of reverse causality. It is more likely that the high murder rate leads to more executions instead of the reverse. In Part 3, we estimate the equation in Part 1 using fixed effects to remove AI. What are the new estimates of the deltas? Are they very different from the estimates from Part 2? We use the xtreg command with the FE option for the fixed effects estimation in Stata. The execution variables become negative, although they are not individually significant at the 10% level. In Part 4, we obtain the long-run propensity from the estimates in Part 3. Is the long-run propensity statistically different from 0 using the usual fixed effect standard errors? We use the Lincoln command in Stata to find the estimate and the standard error for the sum of the 4 execution variables. The estimated long-run propensity is minus 0.146, and its standard error is 0.074. The t-statistic is minus 1.97. and its p-value against a two-sided alternative is 0.048. It suggests that the long-run propensity is statistically different from 0 at the 5% level. In Part 5, we obtain the standard errors for the fixed effects estimates robust to arbitrary heteroscedasticity and serial correlation in the idiosyncratic error term μit. What happens to the statistical significance of the deltas? What about the estimated long-run propensity? We applied the variance-covariance matrix option and specified the cluster robust standard errors. The cluster is at the county level. The first leg of execution becomes statistically significant at the 5% level, and the third leg becomes significant at the 10% level. The long-run propensity of executions becomes more significant now with a t-statistic of minus 3.22. It is statistically significant at the 1% level. Let's do computer exercise 16. In Part 1, we use log wage as the dependent variable and estimate a model containing only an intercept and the year dummies, D81 through D87. Use pooled OLS, random effects, fixed effects, and first difference. What do you conclude about the coefficients on the year dummies? The four estimation methods should give the same coefficients on the year dummies. In Part 2, we add the time constant variable education, Black, and Hispanics to the model and estimate it by OLS and random effects. How do the coefficients compare? What happens if you estimate the equation by fixed effects? The OLS and the random effects give the same estimates for the three time constant variables. The standard errors from the random effects are larger than the OLS. Suppose we use the fixed effects estimation method. In that case, the variables will drop out of the estimation because the fixed effects within transformation will remove all time constant variables along with the fixed effects AI. In Part 3, what do you conclude about the four estimation methods when the model includes only variables that change just across t or just across I? For the variables that are time constant or only change across individuals, the OLS and the random effects give the same estimates with different standard errors. We cannot use the fixed effects method for the time constant variables. For the variables that only change across time or change the same amount for all individuals over time, the time dummies have already captured the effects, and we cannot include them in the model. In Part 4, we estimate the equation by random effects. Do the coefficients seem reasonable? How do the non-robust and cluster-robust standard errors compare? We estimate the model by random effects with usual standard errors and cluster-robust standard errors. From the table, we see that most cluster-robust standard errors are larger than the usual ones, but it does not substantially change the statistical significance of the variables. All the coefficients seem reasonable. Wages are estimated to be higher for union members and married workers. More education results in higher wages. On average, black people earn less than white people, and there's no significant wage gap between whites and Hispanics. In Part 5, we estimate model by fixed effects. How do the estimates of beta 1 and beta 2 compare with those in Part 4? Compute the usual fixed effects standard errors and the cluster robust standard errors. How do they compare? The fixed effects method gives smaller estimates for the union and married variables than the random effects estimation. Using the usual or cluster robust standard errors does not change the statistical significance of the variables substantially. In Part 6, we obtain the time averages for union and married variables. Along with education, black and Hispanics, add this to the equation from Part 4. Verify that the correlated random effects estimates of beta 1 and beta 2 are identical to the fixed effects estimates. We generate the averages of the union and the married variables over time. Then we add the time averages to the model and estimate by random effects. The correlated random effects estimates for the two time-varying variables are identical to the fixed effects estimates. In Part 7, we do the Hausman test. What do you conclude about random effects versus fixed effects? We use the Hausman command in Stata for the Hausman test. We reject the null hypothesis that the estimates are not systematically different between fixed effects and random effects. In other words, the estimates are different because the unobserved individual common factors affect wages and correlate with the explanatory variables in the model. Under the circumstances, we prefer the fixed effects estimation method. We can also choose between the two methods by the F-test for the joint significance of the coefficients on the time average variables in the correlated random effects model. We reject the null hypothesis and conclude that the fixed effects method is better. In Part 8, let education have an interactive effect with both union and married and estimate model by fixed effects. Are the interactions individually or jointly significant? Why are the coefficients on union and married now imprecisely estimated? We use the double hashtags between variables to represent the level and interaction terms. Remember to add the C dot in front of the continuous variables. We estimate the model by fixed effects. The interactions are neither individually nor jointly statistically significant at any reasonable level. The coefficients on union and married also become insignificant because of the collinearity problem with the interaction terms. In Part 9, we estimate the average partial effects of union and married for the model estimated in Part 8. How do these compare with the fixed effects estimates from Part 5? We use the margins command with the dy dx option to obtain the average partial effects of the variables. The results are very close to those without the interactions in Part 5. In Part 10, we will verify that for the model in Part 8, the correlated random effects estimates are the same as the fixed effects estimates. We generate the time average variables for the interaction terms. Then we add the averages to the model and estimate the model by the random effects. We compare the estimates for the time-varying variables in a table. The estimates from the correlated random effects are identical to those from the fixed effects. Finally, we reached the final computer exercise. We use the data to answer the following questions. Use the command xtset, school ID, year, to set the cross-section and time dimensions. In Part 1, how many schools are there? Does each school have a record for each of the 6 years? Verify that the log of average real expenditure is missing for all schools in 1993. We can use the xtdescribe command to get the information of the dataset. There were 1,778 cross-sections. That is 1,778 schools. When we xtset the dataset, we find that it is a strongly balanced panel data, meaning that each school has a record for each of the 6 years. Since the variable log average real expenditure uses the lag of the expenditure, it will be missing for the first time period. We can list the first 24 observations to verify it. In Part 2, we will create a selection indicator S that is equal to 1 if and only if you have long missing data on mass, log of average real expenditure, lunch, and log enrollment. Next, define a variable TOPS to be the number of complete time periods per school. How many schools have all given years of available data? We first generate the selection indicator S. Then we can calculate the sum of the S within each school. We keep the schools with long missing data in all 5 time periods. 922 schools have all given years of available data. In Part 3, we use random effects to estimate a model relating mass fall to log average real expenditure, lunch, and log enrollment. Be sure to include a full set of year dummies. What is the estimated effect of school spending on mass fall? What is its Clark's robust t-statistics? We estimate model with random effects. The coefficient of the spending variable is 7.16. Its cluster robust standard error is 1.85. The t-statistic is 3.86. and its p-value is 0 to 3 decimal places. It implies that if spending increases by 10%, the mass passing rate will increase by 0.7 percentage points. In Part 4, we estimate the model from Part 3 by fixed effects. What are the estimated spending effect and its robust confidence interval? How does it compare to the random effects estimate from Part 3? The fixed effects estimate is smaller than the random effects estimate for the spending effect. And the fixed effects estimate is only statistically different from 0 at the 10% level against the two-sided alternative. So the 95% confidence interval contains 0. In Part 5, we create the time averages of all the explanatory variables in the estimation, including the time dummies. Verify that when you add these and estimate the equation by random effects, you obtain the fixed effects estimates on the time-varying explanatory variables. What happens if you drop the time averages for the year dummies? We generate the time averages of all the explanatory variables, add them to the model, and estimate by random effects. Remember to drop the observations with missing values using the selection indicator before we calculate the time averages. We compare the estimates for the time-varying explanatory variables from the correlated random effects model and fixed effects model. The estimates and the standard errors are identical. The time averages for the year dummies are perfectly collinear with the year dummies, so they drop out from the correlated random effects model. In Part 6, is the random effects estimator rejected in favor of fixed effects? Explain. Yes, we will choose the fixed effects estimation method. We have two ways to show that. First, we use the correlated random effects version of the Hausman test. That is, to test for the joint significance of the averages of the time-varying variables. The F statistic is 74.66 and its p-value is 0 to 4 decimal places. We reject the null hypothesis and conclude that the fixed effects method is preferred. Second, we can do the Hausman test in Stata. The null hypothesis of the Hausman test is that the difference in coefficients between the fixed effects and the random effects is not systematic. We reject the null hypothesis and conclude that only the fixed effects estimates are consistent. So we are in favor of fixed effects. Thank you so much for solving the computer exercises for Chapter 14. I hope I could see you in the next chapter. Thank you for watching this video and subscribing to my YouTube channel. See you next time.